Here we have the third section of the Introduction to Partial Differential Equation Revision tutorial, namely energy methods. This is quite a short section because we do not concentrate on energy methods, particularly in this course. We do use them a little bit to provide an alternative proof of uniqueness and to provide the uniqueness proof in the case of the wave equation. But of course, as in the previous section, we mostly use the maximum principle, which is a bit stronger, to prove uniqueness for the Laplace and heat equations. But nonetheless, in more general settings, the energy methods apply better than maximum principles, or in more situations than maximum principles. And so they can be quite useful in general. In general, they can also be used to prove existence. I'll make a comment on this shortly. But let's just look at what this is. So an energy method, basically you have a functional, which is called the energy functional often. And so it is a certain integral of a potential solution W to produce a number, right? And it can be quite a complicated integral depending on which PDE you're trying to apply it to. So this is the formula for the inhomogeneous Laplace equation, namely the form. You want to look for solutions of this. And so this is the corresponding thing that you examine. And you don't apply it to all functions. You only apply it to functions which meet the boundary condition G, but they don't necessarily meet the partial differential equation, but they do meet the boundary conditions. All right. Sorry, this should be C2 here. Okay, twice continuously differentiable functions whose where the function and or its derivatives extend continuously to the boundary, which meet the boundary condition being equal to some function g. And we can actually see that for the Laplace equation, the integral depends on both the inhomogeneous term f in the formula and on the boundary condition g, which restricts which functions you consider this functional acting on. Okay. The essential point here is theorem 3.25, Dirichlet's principle, which says that if a function is a solution to the Dirichlet problem, then it minimizes this integral. It has value with this integral lower than all other functions in this set. It's a minimizer. Okay. I said that in more general settings, it can also be used to prove existence. The problem is that the set of functions that we're considering here is not a closed set. Okay, because twice continuously differentiable functions, the limit of a twice continuously differentiable function does not need to be twice continuously differentiable. We know that there are continuous functions whose limit is not continuous anymore, for example. So the domain of this is not a closed set, and so there's no reason that there should exist a minimizer on this set. Whereas if this was a closed set and this function, I believe, is continuous, then there would have to exist a minimizer, and then you would have uniqueness. Then you would have existence, the proof of existence. Again, this is a case of the regularity determining being necessary at the outset to determine whether or not a solution exists. We can imagine that if in some more general context, considering more general functions, so that this space where the functional was acting was a closed set of functions, then we could prove existence through the fact that a minimizer had to exist and minimizers solve the equation. But we don't have that here. We will just use this to prove uniqueness. Okay. So we know that if there's a minimizer for this function, then it's a solution to the Laplace equation, and vice versa. Any solution to the Laplace equation with this boundary condition is a minimizer of this functional. So how you prove uniqueness is very typical. Suppose that there were two different minimizers, U1 and U2, and we look at their difference. We have already seen then that, V, which is F, and V would have to be 0 on the boundary. Right? We saw this in the previous section. So if there are two solutions, their difference is a minimizer of the I00, I think you could call it, energy functional, and the minimizer of the I00 energy functional is given by 0. Has 0 as a minimum. And it actually has 0 as its unique minimum, as you can prove from working with the integral. And so therefore V has to be equal to 0, and then U1 is equal to U2, and we've proved uniqueness. Okay. There's also a short calculation at the end of section 4.4 defining the heat for a solution to the heat equation for a body, the total heat of a body, I would say, heat, as the square of the temperature of the body, summed up over the whole object. Yes, and there it discusses slightly different conditions. It just discusses, instead of assuming omega to be a bounded domain, it makes the assumption that U should be square integrable, so it should be an L2 function. And then it does a calculation to show that this is always a decreasing function in time. Okay, why is that important? Because it shows that obviously this function, because it's the sum of a square, has to be greater than or equal to 0. And so if it's decreasing over time, the only possibility if it starts at 0 is that it stays at 0 for all time. And so therefore you can use that to prove that the difference of two solutions to the heat equation is again a solution to the heat equation with energy 0, and the only function with energy 0 is the 0 function. Therefore, the two solutions have to be the same, very similar to for the Laplace equation. And so that might show you, that might give a hint where this function had to be L2. You might want to say that this function, its derivatives should be L2, and then you might want to consider that set, right? The set where a function's derivatives are L2, and you probably need to consider weak functions to make this a closed set, but that's going beyond the course. Okay, so let's then look at the energy for a wave, because this is something that's necessary to get a result we wouldn't have otherwise. So this is theorem 5.7, showing the solution for a bounded domain with initial and boundary conditions for the wave equation has a unique solution. And in this case, the energy functional, E, is given by the square of the change in U in time, and the change in all space coordinates squared as well. So this is similar to the Laplace equation, where you look at the squares of the derivatives. And by direct calculation, you show that E is constant over time. So let's do that calculation now. So the t derivative of E, the domain is not changing, so we just bring this, we make sufficient assumptions that we can bring this inside. This gives us tu and then the second derivative, and then this will be okay, I want to write this as a sum. The sum over the squares of the ith derivative of u squared, 1 up to n. So over all the space coordinates. And of course, when you apply the t derivative to that, you will get like so. So now we can see what we should do because we have here t squared. Yes, so we should use the fact that u is the solution to the wave equation. And as a solution to the wave equation, we can substitute in here that this is equal to the Laplacian of u. And the Laplacian is, of course, all its second derivatives. All right, so we have to be careful here not to confuse squares and second derivatives. Okay, plus yes. And then in the next, and I would say almost final step, what we should do is we should reverse the order of this partial derivatives so that it's I and then t. And then for each of these terms, we should apply integration by parts or partial integration to move this derivative with respect to I onto the other term. So doing that gives us sum over like so. And then we will have minus from the partial integration formula. We will have the second derivative with respect to I. And then what remains here is t. And then you see that this comes out and we have the same term twice and it gets to 0. Okay, so that assumption requires, applying integration with parts there requires some assumption about u vanishing for large things, but that can be part of the assumption of you need some integrability assumption here, right? So if you assume that u is a solution with compact support, then the integrals are guaranteed to exist, and then you also get, for example, that you can apply integration by parts here. Okay, so this shows that E is constant in time. You might want to contrast this to the heat equation where the energy was decreasing in time. But in either case, you see that the difference of two solutions has to have energy 0 and therefore has to be the 0 function. And again, therefore you get uniqueness. Okay, the only thing I would say physically, using the physics of the situation, is how to explain each of these terms here. So this term here is pretty easy to explain. If we think of a wave as being like this, that's a terrible wave, then how u changes in time is it might be increasing or it might be going down. And so this term here is the inertia, or it's the speed that the wave is moving up or down with, and so it corresponds to the inertia or the velocity squared. So this is also called the kinetic term. And then if you look at here, this is a measure of how steep it is. So for example, you might have a wave that is like this, and so the gradient, the value of the wave is changing very rapidly. The gradient is very high. And so you can imagine if you're imagining something like a rubber band, this is very, very stretched. And so there's a lot of energy waiting to be released. And this is called the potential energy then. Right? Just like you have the potential energy of a stretched rubber band, you have the potential energy of the wave. It's being stretched and it wants to return to equilibrium. So that's a type of energy there. So that might help you remember the two terms or understand the two terms in this energy formula. And this is very typical of the energy formula actually corresponding to the energy of the problem when you're thinking of the PDE as describing physics. Okay, so this was a very short section, but that was the main idea. To prove uniqueness using some integral functional of the solution.